Welcome to Let's Get to the Marks, going through a little walkthrough here for you A-level chemistry students, going through AS Chemistry 2019, Paper 1, Inorganic and Physical Chemistry. Takes about an hour and a half to do one of these. This is made up of 8 questions and a Section B multiple choice question paper. Let's get into it. So, question 1. This question's about compounds that contain fluorine. Sodium fluoride contains sodium ions Na plus and fluoride ions F minus. Na plus and F minus have the same electronic configuration. Explain why a fluoride ion is larger than a sodium ion. So, why don't you pause the video, have a go, unpause, and check the answer. Okay, what I'm doing now is I'm drawing out the electronic configuration of the both so you can see that these ions have the same electronic configuration and see if we can get anything from this. If we just look purely at the electronic configuration, we may have a little confusion as to why they're different sizes. We need to actually look a bit further and not look at the electronic configuration, but look at the atomic number, which gives us the number of protons. And sodium has 11 protons in the nucleus, so there's an 11 plus nuclear charge, and fluorine or fluoride ion, as it is here, has 9 protons in the nucleus, and so a 9 plus nuclear charge. Therefore, sodium has a stronger nuclear charge, has a greater attraction to those 8 outer shell electrons, and it pulls them in closer to the nucleus, hence why it's smaller. The fluoride ion, of course, has a smaller nuclear charge. Therefore, there's a weaker force of electrostatic force of attraction between the nucleus and the outer shell electrons, and so those electrons are able to drift away further, making the fluoride ion larger. Now, you can answer this in terms of sodium, but the question does specifically say explain why a fluoride ion is larger, so you might want to do this second sentence here as your answer. Both are worth 2 marks, but this is more the mark scheme one, which is focusing on the fluoride ion and saying, well, it has less protons, so less nuclear charge, less attraction between the nucleus and the outer shell electrons. And there we go. Let's get on to 1.2. Explain in terms of the structure and the bonding why the melting point of sodium fluoride is high. So you all know from GCSE that ionic compounds have a giant ionic structure. And if I bring up the ions again, we can see we've got the sodium ion and the fluoride ion again here. And of course, because one is positive and one is negative, there's an intermolecular force. There's a force of attraction between them. This is a strong electrostatic attraction. It's actually an intramolecular force, but there we go. Strong electrostatic forces of attraction between the positive and negative ion, or the oppositely charged ions, require lots of energy to break. Now, in a giant ionic structure, you're going to have many, many, many of these strong electrostatic forces of attraction that are known as ionic bonds, and you're going to require lots of energy to break them. Hence why it would require, well, why sodium fluoride has a very high melting point, and you don't often see salt melting when you're doing your cooking. All right, let's get on to 1.3. The ion H2F plus is formed when hydrogen fluoride gains a proton, as shown in this equation. HF plus H plus goes to H2F plus. Name the type of bond formed when HF reacts with H plus, a hydrogen ion. Explain how the bond is formed. So we need to name this bond and explain it. So this is known as a dative covalent bond. Oh my gosh, what have I put there? Dative covalent. Oh, whatever. Oh my gosh, covalent. Okay, we got there in the end. Dative covalent bond. You can call it a coordinate bond. It's another name for it. This is when a lone pair of electrons is donated from one atom to another atom that is able to accept a lone pair of electrons to form a covalent bond. In this situation, it's the fluoride in the H2F that is donating a pair of electrons to the positive hydrogen ion. And here's a little example of how. So this little circle is the electron from the hydrogen. It's covalently bonded to the fluorine. The fluorine has 6 other electrons, so 3 extra pairs. Guess what? It can donate one of those pairs to a little hydrogen ion, which is a proton, basically has no pairs of electrons. And that hydrogen ion will come in close, form a covalent bond where both of the electrons are coming from the fluorine and none from the hydrogen. And there we go. That's a dative covalent bond. Okay, let's check out 1.4. Fluoro antimonic, that's a crazy name. Fluoro antimonic acid contains 2 ions, SbF6- and H2F+. Draw the shape of the SbF6 minus ion and the shape of the H2F plus ion. Name the shape of each ion. So this is worth 4 marks. First of all, we can look Sb here, that's the central atom here. Well, it's got 6 electrons in the outer shell. They're bonded with the fluorine atoms that are surrounding it. So there are 6 bonded pairs of electrons. And whenever you have 6 bonded pairs of electrons, you're going to get this shape, which is known as octahedral. And essentially it has a kind of square planar in the middle. So it's like got one plane with 4 atoms coming off of it. You can use dashed lines to show the atoms kind of going back into the paper, and you can use solid black lines to show them coming out of the paper, but not necessary on the mark scheme to do that, but good practice. And then we've got a fluorine atom above and one below, and this shape is known as octahedral. It's essentially 2 pyramids, or like a traditional diamond shape, or 2 pyramids with their bases connected. Now we've got H2F plus, and fluorine is the central atom here. How many electrons are in a fluorine atom? It's 7. However, it's got the positive charge, the plus, so that means it only has 6 electrons around it. How many of those electrons are bonded? 2 of the electrons are bonded with the hydrogens, so 6 minus 2 is 4. So there are 4 electrons that are on their little lonesome, and they form 2 lone pairs. So we have 2 bonding pairs and 2 lone pairs. So we've got 4 pairs around the atom, and when you have 2 bonded pairs and 2 lone pairs out of the 4 pairs, you get a bent or V-shaped molecule, just like the water molecule. So this is very similar to the shape of H2O, and so we just want to draw it like we would a water molecule. So you can see I've shown the dot on the cross here with the hydrogen for the 2 bonded pairs, and then 2 dots for the lone pairs of the fluorine. We can draw those Mickey Mouse ears if we like. I don't really need to show the bonded pair of electrons. The solid black line shows that in itself. I can show the Mickey Mouse ears or the 2 pairs of dots for the lone pairs. That's totally fine. Of course, the aim is that these pairs of electrons want to get as far away from each other as possible. They want to minimize repulsion, and we get a greater repulsion between these lone pairs, and that's why we get that bond angle with the water of like 10, what is it, 107 or 107.5, whatever the hell that is. You don't need the bond angles here, so that's fine. But what you do need, which I nearly forgot, naughty, naughty, is to put the charges of the ions outside in brackets. Don't want to lose 2 marks for that. Okay, we're on to 1.5. Hydrogen fluoride reacts with ethyne, that's C2H2, as shown in the equation. All compounds are in the gaseous state. We've been given the bonds of CH, the triple bond, the HF bond, and the CC single bond, and the mean bond enthalpies of them. We've also been given the enthalpy change of -179. Use the data to calculate a value for the bond enthalpy of the CF, the carbon-fluorine bond in the product. Right, I like to approach these with reactants minus product equals the enthalpy change. We've been given the enthalpy change. We've been given all of the energy for the mean bonds in the reactants and all of them in the products except for the CF. So just set your equation out like this and then solve the equation. So let's start off by working out the total bond energy for the reactants. So we want the ethyne bond energy, so 412, 412, and 837. Smash that in the calculator and then add that to the coefficient here of 2 times HF. So first of all, 412, 412, and 837 equals 1661. I've now got a coefficient here. Don't forget those big numbers. You've got to multiply everything by that. So HF is 562. So I want 2 times 562. Smash those in the calculator, add them together. Oh, what do we get? We get 2785. That's the total for the reactants. So we now minus the product. So I'm going to do 4 times 12 is 1648 plus 348 equals 1996. And that equals an enthalpy change of -179. Hold on. I forgot the 2F. So yeah, we've got the missing CF bond as well. So I get 1996. That's for the 4 CH bonds. And that's for the CC bond. And then I have plus 2CF, and that equals -179. Now we need to simplify. So let's start off by taking, we want to simplify. So let's add no, let's take away 2785 from each side. So I can get rid of the 2785. So first of all, I'm going to minus 2785 from both sides of the equation. And what's that going to give me? Bum, bada, bum, bum, bum. Smash it in the calc. Welcome to Let's Get to the Marks, going through a time of flight mass spectrometry question. You can see the stem of the question here. If you're interested in some more of these, I've gone through the latest one on this link here to this video. That's the latest one by AQA. And at the end of this video, you'll see a couple more videos I've done on time of flight. You might want to work through a whole section. Let's get down. 2.1, describe how the molecules are ionized using electrospray ionization. This is the same for anything that you ionize with electrospray ionization. We're going to use a volatile solvent. We're going to dissolve the sample, the molecules, the compounds into a volatile solvent. Why do we use a volatile solvent? It's not relevant to this question, but the volatile nature of the solvent means that it evaporates quickly after we've added it and before the sample is injected. Now, the second part to this is we inject the sample through a needle whilst passing a high voltage across the nozzle of the needle. And what this does is this creates a positive charge on the compound or the molecule by adding a hydrogen ion or a proton to the molecule. And those are the three marks. So dissolve with a volatile solvent, pass through a high voltage, and a proton's added. Let's zing. 2.2, give the formula of the ion that reaches the detector first in the time of flight mass spectrometer. So if we zing back up, we can see the three different compounds with their molecular formulas, C3H5O2N. What we want to do is work out the mass of each of these because the lightest one is likely to reach the detector first, right? So we've got 36 plus 5 plus 32 plus 14. And then for this next one, we want to do C3H7O3N. So that's going to be 3 times 12 carbons is 36 again. This time we've got 7 hydrogens, so plus 7. This time 3 oxygens, so 3 times 16 is 48, plus 14 for the nitrogen. And then we got C3H7O2NS. So again, we've got 36 for the carbon, 7 for the hydrogen, 32 for the 2 oxygens, and we have 14 for the nitrogen and another 32 for the sulfur atom. Now, if we add these mass numbers all up, we're going to get like, and I might have got this roughly wrong, but roughly, people, we just want to find which one's the lightest. So as long as it's not close, 87 for the top one, and then something like 107, is it for the next one? And then, or 105, and then 121. So the lightest one here is this C3H5O2N that's going to reach the detector first. Let's not forget that it's electrospray ionization and we added a proton. Therefore, the mass will increase to 88. We're not asked about the mass here, but there are questions which ask you that. So the formula is going to be C3H5O2N plus. The plus represents the proton. Some people don't like to just write the plus. They want to write H plus. That's totally fine. H plus or plus, they're both protons, so they're equal to each other. So those are the correct formulas. Okay, 2.3, a sample of germanium is analyzed in TOF, time of flight mass spectrometer, using electron impact ionization, given equation, including state symbols for the process that occurs during the ionization of a germanium atom. Okay, so what's the symbol for germanium? It's capital G with lowercase e. It's going to be in the gaseous phase because we must vaporize them when we're going to ionize them. It's hit by a beam of electrons from an electron gun that adds an electron that knocks an electron off of the germanium. It rams into it and smashes an electron from the outer shell. So we don't just get the electron from the electron gun, but we get the electron that's knocked off as well. So we've got 2 electrons on the right-hand side. Don't forget the positive sign for the germanium. It's now an ion. And the gaseous symbols are important too. Right, moving on to the final part, we're looking at 2.4. In the time of flight mass spectrometer, a germanium ion reaches the detector in 4.654 times 10 to the minus 6 seconds. So we've got the time there. The kinetic energy of this ion is 2.438 times 10 to the minus 15 joules. The length of the flight tube is 96 centimeters, but yeah, so we've got distance and time, and that should make us think of speed equals distance over time. You always need that equation in the time of flight. I've never seen one without where you don't need speed equals distance over time or velocity equals distance over time. And they will always give you kinetic energy is equal to half mass times velocity squared. So let's start with the distance. We've got 96 centimeters. We want to divide by 100 to get 0.96 meters. We want to divide that by the time, which is 4.654 times 10 to the minus 6, not fitting that on very well here. Now that is going to give us the velocity or the speed. Okay, I would keep the numbers in your scientific calculator. I'm going to shorten things down so they fit on my page here because I'm running out of room. So 206,274 meters per second, that's the velocity. So now I know the velocity. I can come over to the kinetic energy equation. I also know the kinetic energy because, of course, I've got the energy up the top here, which is 2.438 times 10 to the minus 15. That's the kinetic energy, or just the energy. Now, what I want to do is rearrange that equation, and there's a half in there. So I'm going to times both sides by 2. So I'm going to end up with 2ke equals mv squared. I'm then going to move the v squared over by dividing both sides by v squared. So I get 2ke over v squared equals the mass. So we're now going to work out the mass. Remember, at this stage, we're working out the mass of the ion, and that's the same in all of these time of flight equations. You first of all work out the mass of the ion. So we're going to do 2 times 4.38 times 10 to the minus 15. That's the kinetic energy. We're going to divide that by the velocity squared, which is 206,274. And then we want to square that. Don't forget to use brackets in your scientific calculator. The amount of times I'm lazy and forget to put brackets and bracket things, and I end up getting the wrong answer, which is what you do if you're sloppy. Most maths A-level students are well trained on using a scientific calculator, but people doing chemistry who don't do maths, they can sometimes make this mistake. So the answer is 1.145971953. Again, just leave it in your calculator or round that to 1.146 times 10 to the minus 25, and that is our mass. But remember, that's the mass of an ion, and it's the mass of an ion in kilograms. The question asks for the mass in grams, so we need to times by 1,000 to convert to grams. All that does is take away 3 zeros, and so we end up with to the minus 22. Notice here I've rounded to 1.146 times 10 to the minus 22. It's not going to affect your answer. It's so close to 1.146 that is good enough. Now that was for an ion. I want to know for a whole mole. Now a whole mole is made up of 6.022 times 10 to the 23 ions. So I'm timesing it by L, which is 6.022 times 10 to the 23. And that's going to give me the mass in grams of a mole, and the mass in grams of 1 mole is equal to 69.012. Now they asked us for the mass number of germanium, so I need to round that to a whole number, an integer, so it's 69. So the answer here for the full 5 marks, bosh, 69. Guys, really, really important you hit the like. It really, really helps.
If you push the button.
Like me.
Would you like it?
Like.
Welcome to Let's Get to the Marks. Going through a little question here on relative atomic mass, electronic configuration, and redox equations. Let's go. Complete the full electronic configuration of a chromium atom. Let's go to the periodic table and work out its atomic number. So if we zip over to the periodic table that you'll have in your data book in your exam, you can see here chromium has the atomic number of 24. That means it's got 24 electrons. So obviously it has 24 protons, and you have the equal number of protons and electrons in an atom, and we're doing the electronic configuration of the atom here. So we want to do 1s2, 2s2. Now remember, you add a new subshell with each level. So When you get to the second energy level, you get 2s2, 2p6. When you get to the third energy level, we've got 3s2, 3p, and then 3d subshell. So you get a new subshell with each energy level. However, we know that the 4s energy level normally fills first. So we would presume here we've already got up to 18 electrons and we've got 6 left to spread between the 3d and the 4s. You would assume that it goes 4s2 because that fills first, then 3d4. But this leaves the 3d subshell partially filled. And it's a much better idea to have a half-filled subshell because that's more stable. So it actually goes 4s1, 3d5. Although the common mistake will be 4s2, 3d4. You want 4s1, 3d5. 3.2. An atom has 2 more protons and 3 more neutrons than a chromium atom, 52. Deduce the symbol, including the mass number and the atomic number for this atom. So if you think that chromium has a mass number of 52 and atomic number of 24, we just look that up in a periodic table. Let's have a little look. We're going to add 2 protons. That means our atomic number, instead of just being 24, is 24 plus 2 because we added 2 protons. So it now has an atomic number of 26. Then we look at the mass number. Well, protons and neutrons have mass, and we've added 3 neutrons and 2 protons. So that's gone up to 57. Now, the atomic number actually tells you what atom you're dealing with. If you change the atomic number, you change the atom. That's why it's called atomic number. So this will no longer be chromium. We need to find its symbol. And if we zing along here, 2 up from chromium, chromium's 24, you'll find iron, Fe. So anything with an atomic number of 26 must be iron, which is Fe. So we're going to now change that, zing back here, and change that to Fe. And that is the symbol. Okay, looking at a relative atomic mass question here for A-level chemistry. So 3.3, a sample of chromium contains 4 isotopes and has a relative atomic mass of 52.09. Table 2 shows the mass number and the percentage abundance of 3 of these isotopes. So we've got 52, 53, 54 and their relative abundances. We then have the question, determine the percentage abundance of the 4th isotope. I'm labeling it Z for algebraic purposes. Show by the calculation the mass number of this isotope is 50. So you've got to recall the equation for working out relative atomic mass, and that is that the RAM is equal to the sum of the mass number times the abundance for each isotope. So we need to times the mass by the abundance for each isotope, then divide by the total abundance. In this case, that's going to be 100 because we're using percentages, and that's going to give us the RAM. Now, we need to set that equation out and then solve it to find our 4th isotope, Z. So first of all, I'm going to set out the equation of mass times abundance for each of our isotopes. So 52 times 82.8 for the first one, 53 times 10.9 for the second one, and for 54, I'm going to do 54 times 2.7. And then that's all going to be over 100, and that's going to be added to, we need to find the percentage abundance, first of all, of our missing isotope. And that's quite simple. We know the total abundance is 100, so we're just going to minus 82.8 minus 10.9 minus 2.7, and that's going to give us 3.6. So we know our missing abundance is 3.6. I'm going to multiply that by my symbol that I was going to use, which was a Z. So I'm using a Z to represent the mass number, which we know is roughly 50. The question tells us that it's going to work out to be 50, but we need to show it by calculation. So we're dividing by 100, and that equals 52.09. So let's simplify this calculation and get to our answer to show that Z is equal to 50. So I'm going to, first of all, multiply out the brackets for all of these. So I've got 52 times 82.8, that's 4,305.6 on my calculator. And then I've got 53 times 10.9 is 577.7. And then I've got 54 times 2.7 is 145.8. So I can add that all together and write a more simplified version, a little neater version, which will be 5,029.1 plus 3.6 times Z. And that is equal to 52.09 divided by 100 for the 5,029.1 and the 3.6 times Z. We're not dividing the 52.09 by 100. Okay, so to get rid of the divide by 100, you know what you do? You multiply both sides by 100. So let's times both sides by 100, and that gets rid of the 100 on the left-hand side, and we just rewrite the equation 5029.1 plus 3.6 times Z, and that is now equal to 5,209 because we multiplied the right-hand side by 100. So what do I want to do next? Well, I want to get rid of this 5029.1. So to get rid of that, I'm going to minus 5029.1 from both sides. And when I minus 5029.1 from both sides, I end up with 3.6 times Z. So we're really simplifying here. And that is equal to 180. And now I know that 3.6 times Z is 180. We're just going to say, hey, I'm going to divide 180 by 3.6. So I'm just going to do 180 divided by 3.6. And that is going to give me Z is equal to 50. And here we go. We've just proven that the mass number of the fourth isotope is 50. And that's going to get us the third mark. Okay, this is an A-level chemistry question on redox equations. So first of all, 3.4, deduce the oxidation state of the chromium ion in Cr2O72 minus. So first of all, how do you work out the redox state? You just always assume that oxygen is -2. There's only one time when it isn't, when it's with fluorine. Other than that, it will always be -2. So there are 7 oxygens. 7 times -2 is -14. We know that Cr2 therefore must be +12 because there's an overall charge of -2. Plus 12 divided by 2 because there's 2 CRs. Each CR must equal +6. And that will get you a mark. Now let's look at 3.5. Iodide ions can be oxidized to iodine using Cr2O72 minus ions. Deduce the half equation to show the oxidation of iodide ions to iodine. So we know from the equation that we've got iodide ions on the left and iodine on the right. We know that iodine is diatomic. There's 2 of them, so I need to put a big 2 in front of my I minus. We know that oxidized means oxidation is loss of electrons, oil rig. So on the right-hand side, I'm showing that loss of electrons, and we know that's going to be 2 electrons. Now we need to deduce a half equation for the conversion in acidic solution of Cr2O72 minus ions to Cr3 plus ions. So what we're going to do here is, right, Cr2O72 minus, I'm going to draw an arrow in the middle, and we know it goes to Cr3 plus ions. Right now, here comes the beauty. There are 7 oxygens. Whenever you have oxygens in a redox equation, you must put water on the opposite side. That's how you deal with the oxygens. There are 7 oxygens, so I need 7 water molecules to balance those 7 oxygens. Now I have 14 hydrogens, so I'm going to add 14 hydrogen ions, and we had a clue from that because it was an acidic solution. It meant hydrogen ions were hanging about. I know I've got 2 chromiums on the left, so I need 2 on the right, so I put a big 2 in front of the Cr3 plus. Then what I do is I add up the charges and I go 2 times 3 plus is 6 plus. I come to the left and I find that I've got a -2 ion and 14 positive hydrogen ions, so I've got 12 plus. I need to add something to electrically balance my half equation. So I'm going to add 6 electrons here, and those 6 electrons are going to reduce the positive charge on the left side to 6 plus. Now both sides are electrically balanced, and this is what you do in all redox. You make sure it's electrically balanced on both sides. So 6 plus on both sides, that's cool. Now what I need to do is combine the 2 half equations to write an overall equation. So what we're going to do here is we need to realize that I have 6 electrons down here at the bottom, and I have 2 electrons at the top. By using the amount of electrons in each half equation, we can write the overall equation. So I need to multiply the top half equation by 3, and by multiplying the top by 3, it means that both half equations are now balanced. So what you need to do is just bring the reactants together and products together from both half equations, but bearing in mind that when you put the top reactants down from the first half equation, we've times them by 3. So instead of 2 iodide ions, I now write 6 iodide ions. I still stick to Cr7O2 minus, Cr2O7, because that's the bottom half equation which we didn't multiply, and 14 hydrogen ions, we didn't multiply that. We know the electrons are going to be 6 on each side, so we're going to cancel them out because we've balanced them. I need to 3 times the iodine because that's part of the first half equation that we times by 3. The 2 chromium 3 plus ions come from the second equation that wasn't multiplied, and so do the 7 H2Os. And boom, we've balanced the overall equation. So guys, I hope that was helpful. One thing that you should always do is electrically check your equations balanced. And if we do that, we can see it's +6, the charge on both sides of the overall equation. So boom, it's done. All right, guys. What I was going to say is don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Here to help you smash your exam. So do me a favor and hit the like button. It helps with the YouTube algorithm. Right, let's get into this one. The first ionization energies of the elements in period 2 change as the atomic number increases. Explain the pattern in the first ionization energies of the elements from lithium to neon. And this one's worth 6 marks. I suggest you grab a pen, grab some scrap paper, pause the video, have a go. Then unpause, watch the walkthrough. Anything you didn't get, make a note of. And that's working smart rather than working harder. So just fix up on your mistakes. Let's go. So as we move from lithium to neon across period 2, and you can see on the periodic table here, the atomic number is increasing. So what does this mean? This means the number of protons in the nucleus is also increasing. So for instance, when we went from beryllium to boron there, it went from 4 to 5, or from boron to carbon, it goes 5 to 6. Now, if you have more protons, that means you have a greater attraction between the nucleus and the outer shell electrons. What does that mean? That means that those outer shell electrons are held more tightly to the nucleus. There's no extra shielding as well because electrons are being added to the same shell, as you can see here with boron and carbon. So electrons are pulled closer to the nucleus. Notice I'm using the E- sign as a shorthand for electrons. Probably best not to in your written answers. All this that we've talked about, the fact there's no extra shielding, the fact the nuclear charge is increasing and the outer electrons are more strongly attracted by electrostatic force of attraction to the nucleus, all of this means the ionization energy, the general trend is an increase in ionization energy from lithium to neon. It requires more energy to remove that electron, to overcome those electrostatic forces of attraction between the nucleus and the outer shell electrons. So this is really, if we answered all of this, we may score 1, 2, possibly 3 marks. Now we need to look at the deviations from the trend. And there's 2 major deviations going across the period. And the first one happens between group 2 and group 3, and the next one between 5 and 6. And now we're going to talk about the deviation between beryllium and boron, which is the group 2 and 3 deviation. Now we would expect boron to have a higher first ionization energy for everything we've written in black there above. That's what we would expect. Boron has 5 protons compared to beryllium's 4, so we would therefore expect there to be greater attraction between the nucleus and the outer shell electrons, and there is greater attraction. But when we look a little bit closer, we're going to see something else that actually changes the order of the first ionization energies. So when we look at beryllium, it has a full 2s subshell, and so does boron, but boron has this lonely little electron in a 2p subshell that is slightly further away from the nucleus at a slightly higher energy level than the s subshell, and of course therefore it has a little bit of shielding from the 2s subshell, and that electron is actually easier to remove than breaking into that full subshell in beryllium and removing that electron. So once again, the reason why boron and beryllium don't fit the general trend of an increase in first ionization energies is because the boron electron is being removed from the 2p subshell that is slightly further from the nucleus and at a higher energy level, and that is why it has a lower first ionization energy than beryllium. So now what does this mean for the marks out of 6 for our answer? Well, the bit in black covers the first 1 to 3 marks. Then you've got the 4th and maybe 5th mark for covering one of the deviations. If you want the full 6 marks, you've got to cover the other deviation. And this deviation happens between group 5 and 6. So we also have another deviation in trends between nitrogen and oxygen. And that's 5 and 6 going across the period. We would expect, once again, for all the same reasons we thought boron would have a higher first ionization energy than beryllium, we'd expect oxygen to have a higher first ionization energy. Why? Oxygen has 8 protons compared to nitrogen 7, so we would expect the greater nuclear charge to pull those electrons closer in, stronger attraction between the outer electrons and the nucleus, so we should think that oxygen would have the higher first ionization energy. However, because two of oxygen's electrons are paired together in one of the 2p orbitals, this means there's extra spin pair repulsion. And this is what you need to do to get those extra marks. You need to talk about the extra spin pair repulsion found between group 5 and group 6, and this accounts for the trend being bucked and there being a slight dip between 5 and 6, where oxygen's first ionization energy is below. So if we look here at the electronic configuration of nitrogen, it has 7 electrons, so 2 in the 1s, 2 in the 2s subshell, and that leaves 3 electrons left. So it's got 1 electron in each of the 2p orbitals. You can call those x, y, and z, and that means that they're half filled. And this actually is a more stable configuration than, say, oxygen's, where it has 1 in each of the 2p's, but then it has that 1 extra electron which has to pair up, and we get spin pair repulsion in that 2p subshell. In that orbital in the 2p subshell, we get some spin pair repulsion, making that electron more easily to remove because it has some repulsion. There we go. This would get you all 6 marks. You've covered all 3 things. So the way the 6 marks were weighted, we needed general trend, deviation between 2 and 3, and then deviation between group 5 and 6. Hope that helped. Welcome to Let's Get to the Marks, going through an equilibrium constant question. Let's get into it.
This time for
Chemistry.
Yeah, baby.
Question 5. Nitrogen monoxide reacts with chlorine to form nitrosyl chloride, NaCl. The equation for this is 2NO gaseous form plus Cl2 gaseous, reversible symbol, 2NoCl gaseous. 5.1, 1.50 moles of nitrogen monoxide are mixed with 1 mole of chlorine, and the mixture is left to reach equilibrium at a given temperature. Now, the equilibrium mixture contains 0.350 mole of NaCl, which is nitrosyl chloride. Calculate the amount in moles of NO and Cl2. They're the reactants in the equilibrium mixture. Now, there's a couple of ways to do this. I like to start by writing out the equation. I know it's a bit of a pain in the bum because the equation's already there, but I write the equation out, and then underneath I draw the little ice board. You might have heard of this before. You write ICE on the left-hand side, and you have a column underneath each of the reactants and each of the products. We've only got one product here. So the ICE, you have I stands for initial moles, C stands for change in moles, and E stands for moles at equilibrium. So my initial moles of nitrogen monoxide is 1.5, and my initial moles of chlorine is 1. What's my initial moles of the nitrosyl chloride? Well, they're a product, and there's no products initially, so that is always going to be 0. However, I have been told that the nitrosyl chloride, we've got 0.350 at equilibrium, and that's all my data. So I know that as it's gone from 0 moles to 0.350, the change in moles for NaCl, or nitrosyl chloride, is 0.35. I can now use that change in moles as soon as you've got one of them to look at the ratios between the product and the reactants and work out how much has been changed of the others. So it's a 1-to-1 with the nitrogen monoxide, so that means 0.350 has been used. However, it's a 2-to-1 with the chlorine. So I put the chlorine here in pink. So we've got 0.350 of nitrosyl chloride, but it has a 2-to-1 relationship with the chlorine. So we need to divide it by 2 to find out the moles of chlorine that have changed, and it's 0.175. So all I've got to do to work out the moles at equilibrium is take the initial moles of the chlorine minus the change in moles, so 1 minus 0.175, and I will get the moles of chlorine at equilibrium, and that equals 0.825. There we go, first of the 2 marks. Now we look at the nitrogen monoxide. We had 1.5 moles initially. We know the change was 0.35 because it was 1-to-1 with the nitrosyl oxide. So I do 1.5 minus 0.350, whack it in the calculator, and it gives me 1.15 moles. So that was the change, that was the moles at equilibrium of nitrogen monoxide. So that's the ICE technique. There's various other techniques you can use for equilibria. I have got a couple of other videos. At the end of this video, you'll see I've got some other videos on walkthrough questions if you want extra practice. you can check them out at the end of this one. So there we go, 2 marks for 5.1. Let's zing on down to 5.2. Give the expression for the equilibrium constant Kc for the reaction between nitrogen monoxide and chlorine to form nitrosyl chloride. Oh my days, I'm going to write the equation out again. So this is just a quick one marker. We're just looking to write the expression for Kc in regards to the equation. So I need to put the equation down again. Now, when you're doing Kc, it's always going to be your products over the top of the reactants. So we're going 2NO plus Cl2 goes to 2NoCl. So I want NoCl at the top and going to use square brackets. Remember, square brackets are for concentration. If you use rounded brackets, they won't give you the mark because rounded brackets is for pressure when you're doing Kp. So we're going to have NoCl, and that is going to be squared to the power of 2 because it has 2 as a coefficient in the equation. And then I'm going to have NO, nitrogen monoxide. Outside the brackets, I'm going to put that to the power of 2 because there's a 2 in the coefficient in the equation. And then times chlorine, which is the reactant, the other reactant. So products over reactants. Let's move on. 5.3 for 4 marks. A different equilibrium mixture is prepared. A different equilibrium mixture is prepared in a flask of volume 800 centimeter cubed at a different temperature. At equilibrium, this mixture contains 0.50 moles of nitrogen monoxide and 0.58 moles of chlorine. For the reaction at this temperature, Kc is equal to 1.32 times 10 to the minus 2 mole per decimeter. Determine the amount in moles of NoCl in this equilibrium mixture. Once again, I'll bust out the Kc expression and the equation because they're going to help me with this. I also need to use the equation N over C times V. Why is that? Because they've given me volume and they've given me moles. So when they do that, I need to convert all of those moles they've given me with the volumes by doing N over V equals C and convert them into concentrations. Those square brackets stand for concentration. Okay, so 0.850, that's the moles of NO, nitrogen monoxide, divided by the decimeters, which is 800 over 1,000. I've just written 0.8, and you get 1.0625. Now, that's moles per decimeter of nitrogen monoxide. And then if we do 0.458 moles of chlorine gas over, or chlorine over 0.8 decimeters, I get 0.5725 mole per decimeter of chlorine. So now I have my concentration of nitrogen monoxide and okay, so let's set this all out as like the Kc expression. So we want to do Kc is 1.32 times 10 to the minus 2. I know that is equal to the product NoCl, which we don't know the moles of yet, over 0.8 moles of NoCl over 0.8 squared. And that is over the top of the reactants, which is 1.0625 squared times 0.5725. So what I need to do is work out how I can isolate NoCl. So how we need to rearrange this, because I can do 1.32 times 10 to the minus 2, multiply it by 1.0625 squared times 0.5725, and that is going to be equal to the products. So as I say, you can keep this all in your calculator. I like to work it all out a little separately, step by step. So 1.32 times 10 to the minus 2 times 1.0625 squared times 0.5725 is equal to NoCl over 0.8 squared. Now, how am I going to get rid of the square sign on the right? Well, first of all, I could actually work out what all my... And this is going to equal 0.00853, which is going to be equal to NoCl over 0.8 squared. Now what do I need to do? I need to get rid of the square. So how am I going to get rid of the square? Well, I can square root both sides. So we're going to zigzag, square root both sides of the equation. That gets rid of the square on the right-hand side. So I'm really doing the square root of 0.00853 is equal to NoCl over 0.8. Oh my gosh, I'm running out of room. And that means I have 0.0926364 is equal to NoCl over 0.8. Now let's get rid of the divided by 0.8. So times both sides by 0.8. And we get our final answer, which is 0.07389, and that is the amount of moles of NOCl. Now, because the 9 is greater than 4, I can round that up to just 0.0739, or you could do 2 sig fig, 0.074. All right, guys, don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, going through a titration question. A student does an investigation to determine the relative formula mass, the MR, of a solid unknown diprotic acid, H2A. Diprotic means 2 protons, so that's why there's 2 H's. H2A plus 2 NaOH goes to Na2A plus 2 H2O. 250 centimeter cubed of aqueous solution are prepared using 1300 milligrams of H2A. A pipette is used to add 25 centimeter cubed of 0.112 mole per decimeter aqueous sodium hydroxide to a conical flask. The aqueous sodium hydroxide is titrated with the acid solution. So the acid is titrated from a burette into the conical flask with the sodium hydroxide. We've been given the titers for the volume of acid that's been added. And the main command for this question is to calculate the MR of H2A, and it's worth 5 marks. What I start by doing is underlining key clues in the stem of the question. Like, we've been given volume and moles, so I'm pretty sure I'm going to need N over C times V. You normally do in titrations. I've been given the mass in 1300 milligrams. It might not be in grams, but it's still mass. And I've been asked to find the MR, so the chances are I'm going to need mass over MR. I'm starting to get this picture, like I might need to use C times V to find N, and then do N times MR to find, mass divided by N to find the MR. So you're starting to get a picture of what you've got to do. It's always difficult to know where to start here, and there's a couple of starting points. And we're going to need to find the mean titer of acid added. So you could start here, or you could start by finding the moles of sodium hydroxide, because you've been given the V and the C, the volume and concentration. Doesn't really matter which one you choose. So I'm going for, let's work out the mean titer. So I found these two are concordant results, 26.40, 26.50. The 26.75 or whatever is way too far out to be concordant. So I'm adding these two together, dividing by 2 to get 26.45. That is the mean titer, and that is of the H2A. That's the diprotic acid. So I now know my volume of diprotic acid. Now, I don't know anything else about the diprotic acid other than its volume. We need to find its concentration so we can get its moles, or we need to find its moles in another way. What we can do is go to the sodium hydroxide now. Even if you're clueless as to where to go next, that's the only viable place, because you've been given the volume and concentration, so you can work out the moles. Now, the volume's in centimeters, so divide by 1,000 to turn into decimeters. We're chemists, we like to use decimeters. We're then going to times this by the concentration, which we've been told is 0.112 mole per decimeter. And this is going to give us the moles of sodium hydroxide that were neutralized with the acid, and it's 0.0028. Now your next step is to go and look at the ratio. We need to find out how many moles of H2A we must have, because we know the moles of the alkali reactant. So we look at the ratio, and for every 2 moles of sodium hydroxide, it's going to neutralize 1 mole of diprotic acid. So what we want to do here is divide by 2. And if you do 0.0028 divided by 2, you're going to get 0.0014 of H2A. That's the diprotic acid. We now know the moles of diprotic acid. We want to find the MR of this. Now, we know the moles in 26.45 centimeters. However, if we look earlier on in the question, it told us that we started off with 250 centimeters of diprotic acid. However, only 26.45 centimeter cube was used to neutralize the sodium hydroxide. So we know that there's 0.0014 moles of acid in the 26.45 centimeters. How many moles are in the 250? How would you work that out? Well, what we need to do is do 250 divided by 26.45 to find out how many lots of 0.0014 moles are in the 250, and you're going to get 9.45 as your multiplier. What you're going to do then is multiply that by the 0.0014. You could just say 250 divided by 26.45 times 0.0014, and that will give you your total moles in the 250 centimeter cubed. Okay, so I'm going to show my working out over here. I'm going to just select a white pen. All right, so once you do 250 over 26.45 times 0.0014, you get 0.013 N. That is number of moles, and that's of the diprotic acid. So that's in the 250. We now know the total moles in the 250. I'm now going to go to the mass over moles gives me my answer, my MR. So I want to do mass divided by moles equals MR. The mass is 1300 milligrams. Now, chemists, we can't really use it as milligrams. We need to change it into grams, and we do that by dividing by 1,000. So it's actually 1.3 grams is our mass. So we're going to do 1.3 over 0.013, and that should give me 98.24. And I might want to round that to three significant figures, so I'm going to leave it as 98.2, or you could say 98.1. It's up to you. I'm sure they're pretty generous on the mark scheme. And that is our final answer. That is the MR of the diprotic acid, 98.2. And here we go. That's going to pick you up 5 lovely marks. 6.2. The uncertainty in using the pipette in this experiment is plus 0.06 centimeter cubed. Calculate the uncertainty in using the pipette. So we actually use the pipette to measure out 25 centimeter cubed of sodium hydroxide. So you just do uncertainty over the measurement times 100, and that gives you the percentage uncertainty. And that is going to give us 0.24%. And it's just 1 mark, nice and easy. 6.3, before adding the solution from the burette in a rough titration, there was an air bubble below the tap. At the end of the titration, the air bubble was not there. Explain why the air bubble increases the final burette reading of the rough titration. So there's an air bubble just below the tap in the burette here. Okay, now once you've added all of your acid, one of the issues we have is the air bubble has gone, but it has been filled with acid where the air bubble used to be. There is now acid. What this means is when we do our reading off the pipette, we're reading from the top down to the tap. So there's this little bit of acid that's not been included in our reading, and it makes us think that we've added more than we have to the conical flask. So basically the acid takes the place of the air bubble, replaces the air bubble, and that volume is we assume that volume has been added to the conical flask, but it actually hasn't. So this makes us overestimate our titra. And that is why the rough titration was larger. So 6.4. During the titration, the student washed the inside of the conical flask with some distilled water. Suggests why this washing does not give an incorrect result. So it's natural to think in your head, hold on, if you've added water, haven't you diluted the concentration of what's in the conical flask? It doesn't matter if you've rinsed it with water and there's a little bit of water in there, it's not fully dry, because you're not changing the amount of moles of sodium hydroxide that are in there. And it's the moles of sodium hydroxide that are in there that are important. That's going to tell us, the moles of sodium hydroxide in there are going to tell us, is going to decide how big the titra is going to be. So it doesn't matter that we've added any extra water in there, it hasn't changed the amount of moles that are inside the conical flask. Okay, let's move on to the next question. So question 7, this question is about the reactions of magnesium and its compounds. Magnesium is used in one of the stages of extraction of titanium. Give an equation for the reaction between titanium 4 fluoride and magnesium. State the role of magnesium in this reaction. So straight away we're told that we're dealing with titanium, and they give us the Roman numerals 4. What does that mean? Well, that means the titanium has the oxidation state of +4 in this compound. We know that chlorine is going to be -1, so that gives us the formula for writing out titanium chloride. So it's TiCl4. We're told that magnesium is used in the extraction, so we want to go plus Mg, draw an arrow, And now the magnesium is going to become magnesium chloride. It's in group 2, so it joins with 2 chloride ions because, of course, magnesium's in group 2, has a +2 charge. So that should be fairly obvious. And then we're going to join that. We're going to have titanium on its little lonesome. Now we just need to balance it. So let's put a 2 here because that gives us 2 magnesiums. But more importantly, it gives us the 4 chloride ions from over there. So there we go. Now I haven't bothered putting state symbols in. What is the role of magnesium? Let's check that out now then. Well, magnesium has a 0 oxidation state there. And whoopsie, over here, the magnesium has a +2 oxidation state. So you've got to ask yourself, what's happened? Well, it's lost electrons. So the magnesium itself has been oxidized. Does that make it an oxidizing agent? No, it doesn't. It's been oxidized itself, but we have to look at what it's done to the titanium to see what type of agent it is. Now, the titanium here is in a +4 state, and over here it's in its elemental form, so 0. So that means the titanium has gained, check out the crusty writing, has gained 4 electrons. And oil rig, if you gain electrons, rig, reduction is gain. The role of magnesium, magnesium has caused the titanium to be reduced. So we will say magnesium is a reducing agent. Okay, let's get rid of this stuff because it's just kind of like bright pink and might be off-putting for what we're doing. So there are the answers there, and that's going to get you 2 marks. Bish, bash. Let's get on with a bosh with a 7.2. A mixture of magnesium oxide and magnesium hydroxide has a mass of 3,200 milligrams. So what I want to do there straight away, oh, not the dreaded pink again, 3,200 milligrams. Now, this is a mixture of 2 substances, it tells us, MgO and MgOH. So magnesium oxide and Mg. Now, hydroxide ions have a -1 charge, so the formula is going to be MgOH2. So combined together, they have a mass of 3,200 milligrams. Look, straight away, I know that they're going to want to convert that into grams. So we're going to want to divide by 1,000 to make 3.2 grams. So if I want, I can put 3.2 grams because we're going to divide by 1,000 for that. The mixture is reacted with carbon dioxide to form magnesium carbonate and water. The mass of the water produced is 200 milligrams. So we've got these 2 reactions, magnesium hydroxide and the magnesium oxide are both reacted with carbon dioxide. Both of them make magnesium carbonate. However, the magnesium hydroxide also forms water. Calculate the percentage by mass of magnesium oxide in this mixture. So we want to know the percentage of magnesium oxide in the mixture, not magnesium hydroxide, sorry, the percentage. Now we can actually work that out as well. If we know that, we're going to know that. Okay, so where's our starting point? Well, we're given the mass of water, so that tells me that we're going to want sort of mass over mR times moles. So let's work out the moles of water. We're given 210 milligrams. Of course, we should really convert this by dividing by 1,000. We want to change this into grams because that's what we should be dealing with. And we're going to divide the mass by the mR of water. Hydrogen has a mass of 1 each, so H2 is 2, and oxygen is 16, so total combined is 18. We're going to divide that, bada bing, bada bang, bada bong, and that's going to give us 0.0116 moles of H2O. Now, you might say to yourself, but why have you worked out the H2O? Well, the H2O is in a ratio of 1 to 1 with the magnesium hydroxide, with one of our constituents of the mixture. So we now know, as it's a 1-to-1 ratio, we also have 0.0116 MgOH2. So we now know we have MgOH2 of the moles of that, we now know we have the moles. I didn't put a little m for number of moles. See, if you don't label it, you get mixed up. Start to think that mg is milligrams, but of course it's not. So we now have 0.0116 moles of magnesium hydroxide. Let's convert the moles into the mass of magnesium hydroxide. And we can do that by timesing by the MR of magnesium hydroxide. And the MR of magnesium hydroxide is 58.3. Why is that? Magnesium is 24.3. Oxygen is 16, so two of them makes 32, and two hydrogens 34. So 34 plus 24.3 makes 58.3. Let's times these together, and they're going to give us our mass of magnesium hydroxide. And the mass of magnesium hydroxide is going to be 0.680, and that is our mass of magnesium hydroxide. So that is grams. So we now have that, and that is Mg, whoa, OH2. Now, there's a couple of ways you can go from here, same kind of thing. If I know that is 0.680 grams, and this is 3.2 grams, then I can do 3.2 minus 0.680, and that's going to give me 2.52. So I'm going to go 3.2 minus 0.680 equals 2.52 grams, and that is of magnesium oxide. So I've got 2.52 grams of that. And all I need to do now is work out that as a percentage of the whole. So I'm going to do 2.52 divided by 3.2 times 100 and see what we get. Smash that in the old calculator and we come up with 78.75%. Now, we want to round to 3 sig normally, so I'd probably say 3 sig 78.7 or 78, in my case, 78.8. And that would be percent. And that is going to get us lovely 4 marks. Super, super, super. So hopefully you got to follow all of that and that wasn't too confusing. There we go. Right, let's zing down, see if there's any more to this question. Nope, that's all 6 marks. Right, we're on to the last question here. So let's have a little look. The following pairs of compounds, each in aqueous solution, can be distinguished by simple test tube reactions. Give a reagent or combination of reagents that can be added to the solutions in each pair to distinguish between them in a single reaction. So we want one reagent that can tell these apart. We've got sodium chloride aqueous and barium chloride aqueous. I'm immediately thinking, what is the test for sulfate ions? If you remember from your AS stuff, we use barium chloride. So let's use sulfuric acid, because when you're testing for sulfate ions, you have barium chloride, and we're going to get a white. Better if I type, isn't it? Let's type that. So we're going to get a white precipitate, and we're going to get no precipitate with the sodium chloride. So there we go. Beautiful. 3 marks. And then down here between sodium chloride and sodium carbonate, we can use a little reagent here. There's a number of reagents we could use. I'm going to go for the old NaGNO3, and this is silver nitrate solution, but I want to make sure it is acidified. Now, the reason why we normally acidify it with nitric acid, HNO3, and the reason is chloride ions form a white precipitate of silver chloride. So we're going to get a white precipitate, and that is silver chloride is going to form. Now, because it's acidified, what do acids do with carbonates? We've got sodium carbonate here. It's going to form bubbles of CO2, or we could say, I can never spell this word, effervescence. I'm sure I've got a couple of extra letters in there for the effervescence. I would find that word difficult to spell. So it's the acidified silver nitrate. We get the white precipitate with the chloride ions, which is silver chloride. If you had bromide ions, it'd be cream. If you had iodide ions, it'd be yellow. And we get bubbles of carbon dioxide with sodium carbonate. So the trick here was to find one reagent that reacts with all. And here we go. That's the end of that. Don't forget to pause the video at the start of each question, grab a scrap bit of paper, write your answer down, and then unpause, watch the walkthrough if you want to see the explanation, or move on to the next question. All right, let's go. Question 9. Which sample measured at room temperature and pressure contains the greatest number of stated particles? Is it 1 gram of hydrogen molecules, 1 gram of helium atoms, 1 decimeter cubed of hydrogen molecules, or 1 decimeter of helium atoms? So what you need to do here is get your old mass over mR times moles. We're going to do 1. Remember, this is hydrogen molecules, not atoms, so the mR is 2. 1 divided by 2, we've got 0.5 moles of hydrogen molecules. Now we want to check out the helium atoms. Remember, helium has a mass number of 4, so we're doing 1 over 4 here, and that equals 0.25. So that can't be the right answer, as there are less moles of helium atoms than there are of hydrogen molecules. Then we've got 1 decimeter of hydrogen molecules. Remember that 1 decimeter is 1/24th of a mole, because 24 decimeters of any gas equals a mole, and that's the same for the helium atoms. So there's 1 decimeter of each, so we've got the same number of particles in C and D, and they're not correct because they're not as much as 0.5. Okay, moving on to the next question, 10. We've got 5 grams of an oxide of molybendium, and they contain 4 grams of molybendium. So essentially, we've got a metal oxide of 5 grams, and they're asking us, what's the empirical formula? Well, we know 4 grams is molybendium. If we look in the periodic table, the MR or AR of molybendium is 96. So we want to do 4 over 96, and that tells us, you can simplify that to 1/24th, or I think that's like 0.041 moles. And then we want to do 5 grams minus the 4 grams for the metal, means we've got 1 gram of oxygen. Oxygen has an MR, well, not really an MR, it has an AR of 16. Its MR is 32 when it's an oxygen molecule. But here we're using the AR, so it's 1 over 16. So we've got 1/16 of oxygen. Obviously, you can tell there from the fractions, there's more oxygen than molybendium. But you're going to want to whack those in the calculator and get the decimal of that. So 1 over 24 is 0.041. You don't really. You could use the fractions if you want. You should be able to tell the oxygen's 1.5 times more. And then we've got 0.0, something like 625 of oxygen. So now we want to divide both by the smallest. So divide both by 0.042. And what we're going to find when we do that is that the molybendium is equal to 1. The oxygen is equal to 1.5. So can you write a formula MO 1.5? No, we need to times by 2 to get whole numbers, integers for chemical formulas. So we're going to end up with 2 for the molybendium, MO2, O3, and that means that C is the correct answer. Okay, now we're going to move on to question 11. Which substance has delocalized electrons? You know this from GCSE, right? Graphite. It's each carbon is bonded to 3 others. It's a group 4 element, so it has 1 free electron between the layers, so it has delocalized electrons. Iodine's covalent, sodium chloride's an ionic compound, and tetrachloromethane's covalent, so they don't have delocalized electrons. Right, 12. Which species is not pyramidal? Right, I'm going to draw out all these shapes. So if we look at A, we've got PF3. Phosphorus is in group 5, so it has 5 electrons. 3 of them are bonded to fluorines, which leaves us with a lone pair. It's pyramidal. Now we've got H3O plus. Right, oxygen's in group 6, so it has 6 electrons. However, there's a plus sign. So it means actually it doesn't have 6 electrons. It's only got 5 electrons in the outer shell because of the positive charge. So we've actually got 3 bonded to hydrogen and then a lone pair, so it has a pyramidal shape. Now let's look at CH3 minus. So carbon's in group 4. So it has 4 electrons. However, what does the minus mean? This means it has an extra electron. So it actually has 5 electrons in the outer shell. So the same as all the others, 3 bonded and a lone pair. It's pyramidal in shape. And then we look at boron. It's a group 3 element. I put G3 there, running out of room here. And therefore, if you only have 3 electrons, you can only make 3 pairs, and they're all bonded with no lone pairs. You're going to be trigonal planar. And that's the shape of the boron trifluoride, or whatever it's called. And there we go. So that's the answer. That's the only one without a pyramidal shape. It's trigonal planar. As there are only 3 pairs of electrons around the central atom, you're going to be trigonal planar. Right, let's look down at question 13. So, which change occurs when water is vaporized? So you've got to remember, water is normally liquid at room temperature and pressure. We want to turn it into a gas. What do we have to do? We have to heat it. We all know that, right? And if you're putting heat in, is that exo or endo? Endothermic is putting heat in. So when you're changing state from liquid to gas or from solid to liquid, that is an endothermic change. You're putting heat in. Now, B, are covalent bonds broken? No, we don't break any covalent chemical bonds when we're boiling things or changing state. However, we do overcome the intermolecular forces. Look here, we've got hydrogen bonding between the different water molecules. That's what we need to break when we want to change the state of water. Does the total amount of energy of the molecules decrease? Of course, gases have more energy than liquids. They're moving around faster, more kinetic energy. So the last one is not true either. Question 14, which equation represents the reaction that has a standard enthalpy change equal to the standard enthalpy of formation for barium chloride? So what we need to think about here, what is the definition for the enthalpy of formation? Can you remember? What are the main factors in the enthalpy of formation? So you should be thinking it's the formation of 1 mole of a compound. So we're looking for 1 mole of a compound from the elements in their standard states. So you can kind of cancel out the ones that don't conform. Like, for instance, let's look at the first one. It's got barium as a gas. Now, is barium a gas? What kind of element is barium? It's a metal, so it's a solid at room temperature. So that's wrong. And then we've got ions in the second equation. Well, they're not elements, they're ions. So the only one that actually conforms is C, because you have barium solid, chlorine gas, and it makes 1 mole of barium chloride solid. D is an ion as well. Right, 15. Which equation does not represent a redox reaction? Right, I'm going to need to zoom in here because we're going to need to draw some oxidation states. So let's get into it. So looking at A, magnesium is in its elemental form, so it has a 0 oxidation state, but in magnesium chloride, it's a +2 metal ion, so it's going to have +2. What does that mean? It's lost electrons, it's been oxidized. So that's redox. Now let's look at oxygen here. It's in its elemental form, and then oxygen is -2 in carbon dioxide and -2 in water. So guess what? It's gained electrons. It's been reduced. That's redox. Let's look at the iron, for instance, here. It's in its elemental form, and then it's in a compound form. That's always a giveaway that we're dealing with redox. And then in this final one, if we write all the oxidation states for the products and reactants, you'll see they don't change. So hydrogen's +1 there, it's +1 on the right and left. Chloride is -1 on both. So nothing changes oxidation state in D, so this is not a redox reaction. Of course, that is a base and acid. That's a neutralization reaction, but there we go. D is the correct answer here for 15. All right, we're going to zing down now and check out number 16. Which property would you expect the element radium to possess? Well, let's zing over to the periodic table and first of all, check out where radium is. So you can see here, radium's right at the bottom of group 2. So what's the pattern as you go down group 1, 2, and 3? What is the pattern? Right, does it form a soluble sulfate? How do I know it doesn't form a soluble sulfate? You should memorize in your head that barium sulfate is insoluble. That's the one we used in barium meals because it can absorb radiation, it can absorb X-rays, and radium is just one below barium, so it's going to have a very similar solubility to barium. So hopefully that's the clue to know that. It does not react with water. Well, what happens when you drop metals in water? You know the coup. They're going to give off hydrogen gas. They're going to react to form a hydroxide. Most metals form a hydroxide, or they definitely react with water, unless you're like really unreactive, like gold or silver. It forms a covalent fluoride. It's a metal, so it's going to be ionic. It's either going to be metallic on its own or form a ionic compound. Is it a good conductor of electricity? Of course, it's metal, so it's going to be a decent conductor. Right, which statement is not correct? Strontium as a blah, blah, blah. Strontium as a blah, blah, blah. We need to check out where strontium is. So we go here to group 2. We see strontium is just below calcium and it's before barium. We're looking at another group 2 metal. So does it have a lower first ionization energy than calcium? Well, let's have a think about that. Strontium is lower in the group than calcium. What do we know about the size of the atoms as we go down? They get bigger. There's an extra electron shell, electrons further from the nucleus, extra shielding, less attraction to the nucleus. No, That's actually true. It does have a lower first ionization energy, and we're not looking for the true answer. We're looking for the not correct answer. So we're technically looking for the false answer here. And the false answer is C. Strontium reacts less vigorously with water than calcium. No, it's going to react more vigorously because the electron's further from the nucleus, easier to remove, hence the lower ionization energy and larger ionic radius. The true answers back that up. Of course, the last one is also a true answer. It is more solid. Hydroxides do get more soluble down the group. You remember magnesium hydroxide is sparingly soluble higher up the group. And as we go down, they get more soluble. Whereas the sulfates get less soluble down the group, so they have like an opposite. All right, 18. Which property of group 2 elements from calcium to barium increases with increasing atomic number? We need to check out the periodic table again. Oh, physics and maths tutor. So why am I going across the period? I'm really looking down. Right, calcium, strontium, barium. So we're looking from calcium, there we go, to barium. Yep, just double checking. So which property increases? Well, atomic radius. Yeah, this one's nice and easy. It's going to be A, isn't it? Atomic radius is going to get bigger. We just discussed that. As you go down a group, you have an extra shell of electrons. There's more shielding. This overcomes the increasing positive nuclear charge because of the extra shielding, bigger distance from the outer electrons from the nucleus. So it's definitely A, and the others are all, yeah, they're not correct. Right. What is the best oxidizing agent? So what we've got to think about here is, what does that mean, an oxidizing agent? An oxidizing agent itself gets reduced. It causes other things to be oxidized. Do you remember oil rig? Oxidation is loss of electrons. It causes other things to lose electrons, and it takes those electrons. It gets reduced. So what we have to do here is look and say, which one of these doesn't mind taking electrons? And the answer is fluorine, one of the best oxidizing agents in the whole of the periodic table. It can even oxidize oxygen. So what about fluoride ions? Let's check this fluoride ion out. Well, this isn't going to want to take an electron. It's already gained an electron. It doesn't want to give it up. Iodine can also be an oxidizing agent, but nowhere near as strong as fluorine, because fluorine's outer electrons are closer to the positive charge of the nucleus. And iodide ions already have their extra electrons, so aren't going to take any more. Okay, let's sing on to this one. Number 20. Some fuel in a spirit burner is burned, and the heat produced is used to heat a container of water. In this experiment, the mass of water is m in grams. The temperature rises Y in degrees. The specific heat capacity is C in JK per gram. What is the amount of heat energy absorbed by the water? Well, this is simply Q equals mCt. So why don't you pause the video and see if you can work out the correct answer. So the heat energy is always Q in our equation, Q equals mCt. All they've done is swap delta T for Y. So we're just looking at m times C times Y, because they've just swapped the symbol that we normally use, delta T, the triangle and the T, for Y. So the first answer here is A. Nice and easy. Right, let's roll to the next question. The equation below represents the complete combustion of butane, C4H10 gaseous, 6.5 oxygens, 4 carbon dioxide, 5 waters, 20 centimeter cubed of butane are completely burned in 0.2 decimeters of oxygen. Which statement is correct? All volumes are measured at the same temp and pressure. What do we know about that? Well, when we're looking at gases, and these are all gaseous, yeah, volume and moles are basically equivalent. So we've got 20 centimeters over 1,000, 0.02 decimeters, or we can say 0.02 moles of butane. The first question, does 40 centimeters of carbon dioxide form? Well, no, the ratio is 1 to 4 between butane and carbon dioxide. So 20 times 4 should be 80 centimeters of carbon dioxide formed. So we cross that one out. We've got 0.065 decimeters of oxygen react. Is that true? Well, we've got 0.02 of butane. All we've got to do is look at the ratio. It's 6.5. So we've got to go 6.5 times 0.02. Does that equal 0.065? Because we know there's a 6.5 to 1 ratio. So we're going to do 0.02 of butane. It all completely reacts because it's the limiting reagent here. And it completely burns in oxygen. So 0.02 times 6.5 equals 0.13. Nope, it's not the right answer, because we make 0.13 decimeters of oxygen. 70 centimeters of oxygen remain. Let's check it out. Well, if we know that 0.13 decimeters of oxygen are used and there are 0.20 at the start, take 0.13 from 0.20 and we get 0.7 decimeters. times 1,000, folks, to put into centimeters, and it equals 70 centimeter cubed. So yes, C is the correct answer. And then we can look at the last one. Is that right? 0.5 decimeters of steam are formed. It's a 5-to-1 ratio with the butane. So if you do 0.02 for the butane of decimeters times 5, we're going to get 0.1 decimeters, not 0.5. So yes, it's not correct. Okay, yeah, let me change that. That's supposed to be sodium hydrogen sulfate. And what else does it form? Well, the other hydrogen from the hydrosulfuric acid is joining with the chloride ions. So the chloride ions are acting as a base. They're accepting the hydrogen. This is not a redox reaction. So yeah, sodium chloride reacts with chlorine when added to bromine. No, you know, with the halogens, they get less reactive down the group. So there's no way bromine can displace chlorine. Chlorine's above it, it's more reactive. Yeah, bromine cannot displace chlorine, it's less reactive. Sodium bromide forms bromine when added to concentrated sulfuric acid. This one is true. So what happens in the first reaction with sodium bromine and sulfuric acid is it's not a redox reaction, it's an acid and base reaction. And essentially, again, the bromide ions act as a base, they accept the hydrogen of the sulfuric acid. However, because of its extra reducing power, the hydrogen bromide reacts with some extra sulfuric acid, and we get bromine formed. I think it's sulfur dioxide and water, but you know, I might have to correct me on that one. Essentially, though, yes, it can be the extra reducing power of the bromine means you can get bromine formed. Of bromide ions, sorry, means you get bromine formed. Right, solid bromide ions form bromine when added to iodine. No, iodine's lower down the group. It cannot displace bromine. Bromine is higher up in the group. So yeah, that one's incorrect as well. Okay, last question in this pack. What is the percentage yield when 20 grams of aluminium are produced from 50 grams of aluminium oxide? This is an old GCSE reacting mass style question. So you got 50 grams of aluminium oxide. First thing to do, and we've only made 20 grams of aluminium, but we need to know how much aluminium we should have made if we had 50 grams. What's the maximum amount of aluminium made? So we need to work out the moles of aluminium oxide, look at the ratio, and then predict the moles of aluminium we could make, convert that into mass. So first of all, 2 times 27 for the ALs is 54, plus 3 oxygens is 48. Whack them together is 102. That's the MR of aluminium oxide. 50 divided by MR, so mass over MR gives me moles, 0.49 moles. It's a 2-to-1 ratio with the aluminium. It's 2 to 4, but same as 1 to 2, sorry, 1 to 2 or 2 to 4. So I'm going to make 0.98 moles of aluminium if all goes well. What is that in grams? So I'm going to times moles by the MR of aluminium, or AR, I should say technically. And that's going to give me like 26 point something grams. That is the maximum amount of aluminium we should be able to make. Now, obviously, we haven't made that. We've only got 20 grams. So let's do the actual mass we made over the maximum amount we could make times 100, and that will give me my percentage yield. So 20 divided by 26.47 times 100, and that's going to come up at like 75.5 or something around those lines. And the lines, oh my God, I can't talk. That's going to be A is the closest answer to that. So that's the correct one. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.